a couple weeks before, I managed to deploy faulty code, and I put our production servers down. And believe me or not, I had to stay late after work to fix them. And believe me or not, I have better to do than fixing broken production after work. I knew the risk. But why was it so important to deploy it that fast? And what gave me the confidence to deploy the code on Friday? And last but not least, why the heck was I thinking to test something on production? We'll come to this, but before we do it, we need to take a few steps back. TopTal. TopTal is a freelancer network that helps companies hire freelancers and scale their teams. I'm not a freelancer there. I work in a core team, and the core team develops our core tools. And the heart of our core tools is the TopTal platform. It's a Rails application of over 1 million lines of code. There are thousands of users using it. And there are hundreds of engineers working, developing this platform on day-to-day basis. So it is a monolith, and it is majestic. I work for a billing extraction team because our monolith has majestic monolith issues, and we plan to extract part of it into services. And our team, the billing team, tries to take billing code, billing domain, and put it into a separate service. We are on the bleeding edge of the service extraction in our company. And we need to do this, but we can't disrupt day-to-day operations, and we can't make the life of our fellow engineers harder. So the bank extraction is out of the question. We decided to use step-by-step approach to make it safe and to avoid disruption. So the first step was to extract the billing code and put it into a Rails engine and still communicate with it using regular Ruby calls. Next step was to actually test the external communication, the network communication. So implemented a sync API using Kafka. We won't be talking about this, even though it's very interesting. And we also added synchronous communication over HTTP and REST. And that's the topic of this talk. To make it safe, we added two important features. First of them was a feature flag that decided if any given request should be routed through REST or should use a direct call. And in case this REST call failed, we added a safe fallback. So if the REST calls failed, we were using a direct call as a fallback. And to end users, the call might be slower, but it was still correct. It was our first approach, and we and to dive a little bit deeper, let's take a look at the models, how it looked. We had product class and billing record class. Let's focus only on those two. And before the extraction, they were associated using regular active record relations, has many and below. But after the extraction, we still had to connect the data from product that stayed platform and billing record that was moved to the billing service. But we couldn't do it with active record associations. So we added an active method to product that was fetching billing records using billing query service that was wrapping all the communication. And we replaced billing record active record with a plain old Ruby object that was connected to product using active record query, but by product ID. And we deployed this, So before we even started, we had a safe environment when we can ensure that in case there are any issues with our API, we fall back to a direct call, and also that we can decide if we use those remote calls using feature flags without deployments. So we deployed it and we enabled the HTTP calls for small percentage of the API, 10 or 20%, and we tried and we failed miserably. Let's try maybe this time. No, it fails every time. The performance of this solution was abysmal. Even for a small fraction of the traffic, we saw a lot of timeouts, and the code was generally slow, and we knew we had to change it massively. And I think it's quite a good moment for a software engineer, right? Everybody loves those optimization projects when you relic and you take a look at the traces and then you optimize and you see how it worked. And that's exactly what didn't happen, because we realized that we can't just optimize current approach. In the middle of our massive refactoring of service extraction, we decided that we need another massive change, that was switching from HTTP API to GraphQL API. And this change we also performed in small steps. So we introduced another layer of feature flags that allowed us to switch between correct, although slow, HTTP API and experimental GraphQL API. And we also added a fallback so that in case GraphQL call is slow, we'll call billing logic directly. And we did think to our standard monitoring errors with rollbar or Sentry, performance with New Relic, we decided that we need something more fine-grained. So we logged every request to our Elastic Stack, and we logged its method name, argument, stack trace, response time, and if needed, an error. And it gave us high visibility. We were able to spot which methods slow and recreate those slow calls locally. We were able to see the source of those slow calls or the source of multiple calls, so that we were able to notice when are the n+1 queries. We were able to spot the errors and reproduce those errors locally and fix them with confidence. So we started with those two strong pillars. We had safe deployment environment, and we had good monitoring that allowed us to control and to decide if we really improve our code, our solution. And those two strong pillars, let's dive into the main phase, the optimization phase. The first thing that we noticed was that several views or sidekick jobs generated a lot of billing requests. It could be thousands of billing requests from a single page rendering, single sidekick job. It was unbearable for the billing service. It wasn't reasonable to serve that. So what happened there? It was exactly like an n+1 problem issue with the database access. It was not very easy to spot those issues, because when you took a look at the job, it was just iterating over products and in batches and calling business logic on them. But then when we looked into the business logic, it was using billing records for products. So for every iteration in the job, we were calling billing service, and that generated that flood of requests and n+1 requests. So what we did, we decided that we should resign from this active object approach when we do external request when we access data, we should reload it one level higher. So we implemented caching, preloading and caching records inside the job. And let's take a look at this cache billing records method. It did three things. First of all, it was fetching records from billing query service. Then it was indexing them by product ID, and using this index, it was assigning billing records to respective products. And because of that, when we did the actual billing business logic call, we weren't doing additional requests to billing query service. So instead calling billing service once per iteration, we were calling it once per batch. And that means instead of making thousands of requests, we did a dozen or half of dozen. And that was definitely a big improvement. So what we learned here, that if we have flag requests, we need to recreate what database does and what ORM ORMs do. We need to preload data, cache them, join them with data that we have locally. And actually, what we implemented really resembles the hash join algorithm that's known from databases. So it was the first issue. Another issue that we noticed was that there was a single field that was requested about 1,000 times per day, and in the worst hours it were hundreds per hour. So it was a lot. We weren't able to preload it because it was in the different requests. So what we did here was we devised a very smart plan. We decided that we can do smart caching. We can add this field to our Kafka events, then we can build a projection on the platform side. And after backfilling historical data, we can start using this projection, this read model, and then we can remove the billing query. That was smart. That was fancy. And I was really happy that I started to do this. But then after a few firsts, Samuel, our colleague that is really into billing domain, came and said, guys, I guess that we have this field on the platform side. Let's check it. And in this moment, I was really annoyed because, wow, that's such a nice approach to this Kafka. And when we switch to this other approach that's not so fancy, and this building read model, it's so cool. We could even talk on a conference about it, right? But yeah, we decided to check the Samuel's approach, and it proved really good because we were really able to use this local field. So instead of spending 2 weeks of building this solution with Kafka, we spent 2 or 3 days mostly talking with developers that were into the billing domain and with product people, and by making huge SQL queries comparing data from those two sources. And we replaced this external call with a single database call. And when we deployed it, the flood of requests was gone. And that was solution because we did it not only faster, but what we did was also more maintainable. Instead of lines of code and asynchronous communication, we did a single liner with a single database query. What we learned here, I learned that while technical excellence can help us winning optimization battles, domain knowledge can let us avoid those battles at all. And that's really wise. After those two issues, we noticed another one. It wasn't about making too many queries. It was about making queries that are really, really slow, at least some of them. What was the reason? When we were building the REST API, we wanted a minimal surface. So it was a universal API returning every piece of data that could be probably needed on the platform side. What does it mean? It means that we were returning about 40 fields and about 3 or 4 associations with potentially hundreds of records. Whenever we needed something on the platform side, we were fetching those. And for our worst products with a lot of billing data, we were sending a lot of data at work. And to make it even worse, we had filtering on the platform side, on the client side. So what we did, we leveraged the power of GraphQL, and it was the moment when the decision to move to GraphQL really, really paid off, because we were able, after implementing the types of GraphQL on the server side, we were able to create customized queries, fetching only the data that was really needed without additional changes on the server side. So instead of fetching 40 fields and hundreds of associated objects, we are fetching 4 fields, and it was blazingly fast. And of course, we implemented filtering on the server side to fetch only the data that is needed. And it worked like a charm during our tests. And I must say that I was implementing this. I was really into this process that we monitor. Then we decided how to optimize it. We optimize and we deploy to production, and we see how our stats are getting better. And it was really, really rewarding experience with a short feedback cycle. And I expected something similar here, and even bigger than usual, because this change was significant. So I merged this, and I was waiting to see the stats. By the way, do you know what was the hottest day last summer, at least in the northern part of our globe? I remember it well. It was 26th of July, Tuesday. I merged my code, I deployed it to production, and I was waiting for those stats to get better. I enabled the feature flag. And I was casually checking Slack when sometimes someone wrote that Sidekick workers consume too much memory. I thought, oh, poor infra guys, they have to work on this. And someone else said that we have failing staging deploy. And I thought someone was reckless and managed to match a faulty code. That's very bad. And then someone told me directly, man, I think it was your code that's faulty. And I thought, it's not possible. It's tested. But I started checking it. And then someone asked us if platform is okay, someone from the business side. And then someone set us folks platforms down. And I knew it was my pull request that did it. And I felt cold sweat on my back. It was the hottest day last summer, Tuesday, 26th of July. How bad was it? It was really, really bad. We consumed about 20 times more memory than usual. CPU utilization was about 10 to 20 times higher than in normal times. So normal times are so flat that they are almost invisible on those charts. And to make it worse, queries to Postgres took about a minute to query Postgres. That was quite terrible. And then 2 good things happened. The first, infra folks reacted without my intervention. They, when they decided that it was the faulty build, they reverted it and then so that the platform returned to normal operations. Then they assisted me in reverting this on master and deploying the new version. So we have green master again. And the second thing, the very next day I started providing a fully fledged fix, and my manager approached me. And you can imagine what a manager could say in this case, a little bit of blame casting, or at least, oh, be careful the next time. And what he said, what Jose said was, good job. I was really surprised. Was it really for me? And he said, yeah, it was wrong that the platform was down, but it happens. And as long as you stayed to fix it, it's okay. It's a good job. And I realize it's also the part of our safe deployment strategy. It's okay to make mistake as long as you are committed to fix it. And that was really, really good experience. So what really happened? During implementing this feature, I did a small refactoring, and I added parameter sanitization. And I was a little bit too eager. So the 3 types of parameters were allowed, but I allowed only 1. And so if someone requested billing records for a client, it was set to nil because of this sanitization, and with no parameters, those calls did nothing, and we were asking for all billing records, and then for all associated objects, and those are millions of records, and that's why we killed Postgres, and then we killed our workers. And I don't think we reached the moment when all the objects were instantiated and then serialized and pushed to network. I basically killed the service. The fix was pretty simple. In case the list of parameters is empty, return nothing instead of returning everything. So we resigned from the SQL default of returning everything when no were close. How did it happen that it slipped through our safe deployment strategy, through our CI and so on? It was, first of all, I was testing only one of these parameters in my unit tests, and it happened to be the parameter that was correctly sanitized. Second of all, we had a feature flag for this, and I switched it off when we noticed production issues, but the bug was introduced in the REST branch, in the safe branch, battle-tested one, so I made it even worse. If I switched to GraphQL, it would have been better, but I didn't know it then. So that's how it worked. That's why it happened. Of course, I fixed the sanitization. And what was the result of our fix, finally? It's the situation before the fix, and it's the chasm when I was fixing issue. And after the fix, the response time is not only better, but it's also more predictable. So underfetching and custom queries really helped us here. But what I really learned here is that no matter how much I trust myself and my unit tests and my feature flags and my reviewers, I should always test manually. We have this rule, this field in pull request template, how to test this. And in this case, I put simply trust the specs. And I think it was a mistake. I should provide a simple test scenario in Rails console and with some expected log output or something, because I believe we could have caught this on development machines or during reviews. And without this manual test strategy, I failed. I broke production. Okay, that was the bad part. Something better. right? The bugs were committed. Now let's do something. After all those changes, we were able to enable this GraphQL traffic for bigger percentage of our requests, and we noticed that every Sunday we had 4 to 9 too many requests error reported by our clients. What happened? Every Sunday, we were first scheduling reminders and then sending them at 5 p.m. And when scheduling, we were doing a lot of requests to billing service. So we fixed it by preloading. It was something we knew well, and we deployed it. We waited for Sunday because we weren't able to reproduce it locally because the issue was generated by Nginx on our production setting. And after on Monday morning, we saw the same issue. Why was that? The error was raised not only during scheduling, but also during sending the reminders. We thought it was we would be covered because the reminders were sent in our talents, in our users' time zones, so not all of them at the same 5 p.m. And we thought, okay, we'll split it into 24 buckets and it's okay. The issue is that a quarter of our talents live in the same time zone. So when evening at this time zone came, we were sending too many requests to billing. We couldn't move our talents to other time zones, so I decided to move the reminders a little bit. Instead of sending them at 5 p.m. sharp, uttered them, adding jitter of 2 minutes. And we calculated that it should be okay, so we deployed it and waited for Sunday. On Monday morning, we saw the same error. Why was that? We missed one more reminder, so we did the same, and on Monday morning, the same error. And it was a month of fixing this because we had to wait every time we had for this time we realized that it wasn't a problem with our domain knowledge. This time it was a technical details of Sidekick. We thought that Sidekick would run our scheduled jobs with 1 second resolution, but in fact, Sidekick did it with about 15 seconds. So instead of having 100 small buckets with requests, we had 8 big buckets of requests. And that was the issue. So we took a Sidekick limiter for Sidekick Enterprise. From Sidekick Enterprise, we implemented window limiting and deployed it and waited for Sunday, and it worked. And it was marvelous. And I must admit, I must confess that it was during this saga when I saw a green build on Friday, and I knew that it must be deployed before Sunday. And I deployed it at 4 p.m. on Friday, and it worked. And I went home at 5. And to make it more interesting, I did it twice during this process. At the very beginning, in the first week, and the very end of this process, and both time it worked Friday afternoon, and I was safe to go home. And it was good to see it finally fixed. So to sum up, what we did, we leveraged safe deployment strategy and good monitoring to be able to apply a couple of fixing of optimization patterns. We were using preloading to avoid N+1 queries. We moved filtering to server side, and we were using custom queries to underfetch data to fetch only what is needed. We tried to use local data, and we spread the load with jitter. And when you take a look at this list, it might sound familiar. I guess that most of you used those patterns, or at least seen them. Let's take a better look at them. Preloading to avoid N+1, that's something that every ORM does. server-side filtering is quite common in Rails to move from find all to where. Both things we implemented not in the database world, but in microservice world. We moved, we applied those both patterns for GraphQL API using local data. It's browser optimization primer to avoid requests if it's possible. Under fetching is something that's built in SQL. Again, we use GraphQL features to use it in the service-oriented world. And spreading the load, I read about it about 10 years ago or something in a high scalability post about YouTube architecture. So it's not that we invented something new. So why do I keep you here for more than half an hour? We are applying something known in a new setting. And why didn't we do it well from the beginning? The answer here is threefold. It was about learning, simplicity, and trade-offs. We realized that it's really hard to spot performance issue simply by staring at the code. We realized that you need to apply traffic of the production shape to your application to see where are the performance problems. And it's really hard to, in many cases, it's really hard to do it locally. The second part of the answer is simplicity. We started with the simplest thing that could probably work. We started with a boring REST solution and with the API of the small surface, of the minimal surface, and only then we moved to something more sophisticated like GraphQL and custom queries. And finally, it's all about trade-offs. When we were implementing the jitter, we had to convince our colleagues from feature teams that it's really required to spread this load and that we can't really do everything at 5 p.m. sharp, because what they really wanted was the requirement is to send a reminder at 5. Let's send it at 5, not sometimes around 5. We had to explain them that it's impossible because we would kill the billing service. So that was it. It was about determining what known patterns we should use in our novel setting. It was about understanding the trade-offs and about applying our knowledge in our specific case. And I shared what we learned. I shared our story about our solutions. I detailedly shared about mistakes. So you don't have to repeat the mistakes that we made. You can go to your work and commit your own mistakes, but then please come back to a meetup or to a conference or anything like this one and tell your story so that we can all learn from your mistakes. And if you wonder if you are ready to do them, if it's safe to do them, just think if you can deploy your code on Friday afternoon. Thank you. I'll answer any question now.